Hello everyone, in this recording we will be estimating log regression model. The question is, why do we need to do log transformation? Or not a transformation, a regression maybe. One of the reasons is transformation. I mean, the coefficients in the log model can be interpreted as elasticities here. And this when you do log. For a 1 unit change in the independent variable, the percentage change in the dependent or the predictor variable is given by the coefficients b1, right? Or b2 if you're talking about the second coefficient, the second predictor, and so on, or the third b3 and so on. So we are measuring basically the elasticities here. There are other usage for the log. They're kind of handling nonlinear relationships, reducing skewness, normalizing residuals, and other usage. In this example, we are going to use it for elasticities as we did in the explanation for the lecture. So economists, after examining the relationship between the inputs of a production function and the resulting output, a common way of modeling this relationship is referred as Cobb-Douglas production. This function can be expressed as the following. The log of q is equal to beta naught plus beta 1 log of L plus beta 2 log of k plus epsilon. Q is the output, L is the labor, and k stands for the capital. First, we're going to load the dataset. I have to first clean everything. So to load the dataset, it's chapter 8. The sheet is production function. This is my data. We have 48 observations. Look at the data. We have QLK. Explore the data. They're all numeric. Look at the range of the data. The Q has a minimum of 1, maximum is 8,762, and L, the minimum is about 1, maximum is this, K is the same thing. So we have a quite range, big range for the first two compared to the third one. So first part says estimate, so we have to estimate this model and see what's going to happen. And the question says, what is the predicted change in output if the labor increases by 1% holding capital constant? So that's why we are doing log, because the way that we're asking about the changes of the percentages for both, right? For the response and for the predictor. First, let me just for curiosity build the linear model. LM Q is our function. Response, my data, summary, L model. Q is not there. Why? Did we run this one? Again, comma. I keep forgetting the comma. So this is the one. We have, again, adjusted R squared is misleading here. Is it tricky? This is for the log. No, it's for the Q, basically. It's 0.9. It's for the Q. 0.9. And the two variables are significance, right? So let's run the log model. So let's run the log model. So log model is LM log Q tilde log small log is a function, so small letters, log K from my data. Okay, run this. So this is the model. These are significance. The R squared is 83%. Someone's going to tell me, but this is 99%. This is maybe kind of overfitting problem here, by the way. We have to do more investigation for this function, for this model. Okay, so I'm going to leave it. It's just beyond my class today. So to interpret this, or to determine the predicted change in output if labor increases by 1% while holding capital constant, we look at the coefficient of the log L, right, which is 0.70. So what is the interpretation is that 1% increase in labor, 1% increase in the L is associated with an estimated 0.70989% increase in the predicted output, assuming the capital remains constant. So if you increase the labor by 1%, you could predict an approximate 0.71% increase in the predicted quantity, or the Q is the output, or what do we call it here? The output, yeah, right? So this is the interpretation, and this is the answer to the question. Let me write this down. We pause. Yeah, so this is everything for this part. After that, you can do net this one, and save it. That's it. Thank you.